Welcome to Atoms and Elements Part 0. This will be our introduction to atomic structure. Let's get started. Now, one of the most important concepts that we need to really become comfortable with right away is the idea of electrostatics. It's also referred to as Coulombic forces, but we'll just stay with electrostatics. Okay, and this is what this is. It's about charge. So charge drives everything in chemistry, all right? So opposites attract. So when we have opposite charges, they cannot resist each other. They want to be together. And it doesn't matter what the circumstances. Positive and negative love to come together. And likes repel. So whether we have two positives or we have two negatives, they do not want to be next to each other. So they are going to repel. And so this idea of electrostatic attraction and repulsion is a driving force in everything we're going to look at. And so as we begin to talk about the structure of the atom, I want you to think about and keep in mind the dynamics between positive and negative charge. All right, this is a dance we're going to follow all semester. Now I'm going to go through a little history here. Don't worry, this isn't a history class. Don't worry about memorizing any dates or anything. I think that the historical context gives us a sense and reflects the structure of the atom. So we're going to look at it in that context, but don't sweat the dates. All right, so we have been debating what we're made of at a physical level, at a metaphysical level for centuries, for millennia, right? So the word atom is very old. It comes from over 400 BC, right? It comes from the Greek word atmos, which means uncut or indivisible. And it was coined by Democritus, right? Because he was a proponent of discontinuous matter concepts. So what exactly does that mean, discontinuous matter? Okay, so I'm going to do a little demo here for a moment. So let's look at this pencil, right? So back in Democritus's time, there was a big debate, right? So one group of people said we could cut this pencil in half and cut this pencil in half and cut this pencil in half, and we could cut it in half into infinity. And we could never stop. We could cut it in half as long as we wanted. But Democritus said no, that if we kept cutting, eventually we would get to this atmos where we could not break it down any further. And so at a chemical level, Democritus was correct, and we call it the atom today. All right, let's see what else happened. All right, so then, you know, just remember, no computers, no internet, no age of information, all right? So 2,200 years later, Dalton, very thoughtful man, he is observing and thinking about what we know to date, and he comes up with an atomic theory, right? He says elements are made of tiny particles called atoms, right? He agreed with Democritus. All atoms of a given element are identical. So this first one, we still hold as true. It turns out this aspect of the theory is wrong. The reason for that is isotopes. We will come back to those. Those are important. Dalton also said the atoms of a given element are different from those of any other element. That's absolutely true. Atoms of one element can combine with atoms of other elements to form compounds. This is true. And we talk about the compounds as a fixed ratio of atoms. And then last but not least, atoms are indivisible by chemical processes, right? So they're not created or destroyed. Now, okay, so we will talk about nuclear chemistry in this course, and then this does not apply, right? So right now we're talking about chemical processes. Okay, so it took a long time to make a significant progress from Democritus to Dalton, but then in about 80 years, J.J. Thomson, he showed that atoms contain negative particles, right? So here's that dance of charge that we started to talk about at the very beginning, right? So electrons are a lowercase e with an uppercase minus, right? There's our electrons. But then atoms are neutral. So if atoms are neutral and we found an object within them that has a negative charge, then there must be something that has positive charge. And so those are the protons. Interestingly, for some reason, we don't put the plus on the P for protons like we do the E for electrons. I don't know what that's about, but just so you're not expecting it, okay? So we just know the protons are +1. Okay, so then in about the same time, Lord Kelvin, who we've named a temperature unit after, he proposed the plum pudding model for the atom. And I like to bring this up because I think it's important. It shows that theories come and go. The plum pudding model was the state-of-the-art theory for a decade. And Rutherford, he was really exploring Kelvin's ideas about this plum pudding model, and so he did an experiment. So let's look at how Lord Kelvin's theory and Rutherford's, how it all comes together, and the experiments help us sort it out. All right, so this would be the Kelvin plum pudding here. Okay, right? So you could think of this, so plum pudding was a dessert, basically literally a pudding, whoops, 2 Ds, with raisins in it. The modern day equivalent would probably be a muffin with like chocolate chips or raisins or blueberries, right? So according to Kelvin's theory, the positive charge was the plum pudding, all right? And then the electrons were the little raisins or chocolate chips nestled into the muffin or the pudding, all right? So then Rutherford went to test this atomic theory. So what did Rutherford do? Well, he took a source of alpha particles, and just to let you know, alpha particles have a +2 charge. All right, and so we have this beam of alpha particles, and then he put a thin metal foil. And so Rutherford said, well, if the plum pudding model's correct and the positive charge is delocalized through the entire atom, then the positive charge of these alpha particles will just sail right through the atoms in the metal foil. And initially, that's exactly what happened. Most of the particles passed straight through. So it looked like the plum pudding model was the correct model. But the longer Rutherford did the experiment, he started to notice that, ding, there started to be some exposure here and here from these alpha particles. So these alpha particles were getting scattered. So remember, if we have 2 positive charges, they repel each other. So what Rutherford observed was that there was localized positive charge causing these alpha particles to reflect or be deflected. And that led to Rutherford's nuclear atom. And so we all know that this is still the accepted form, right? So now we know that the positive charge is localized in the nucleus, and then that's what causes the deflection of the alpha particles. However, it's important to keep in mind, right, that most of the alpha particles still sailed straight through, all right? So if the nucleus, that means there's a lot of empty space, all right? So let's say we made the nucleus the size of a grape, all right? Then if you imagine the nucleus as being the size of a grape, the electrons, right? The electrons are up to 1 mile away. All right? So basically, atoms are mostly empty. Why does it feel so hard, right? It feels so hard, we're going to see, because those electrons are busy whirling about. So, right? So the solidness that we feel really is an illusion. We are mostly empty space. All right. Keep going. So like another 8 years later, Rutherford determined that the proton had the same magnitude of charge as the electron. So that's really helpful. So we're just going to call them plus and minus 1. And then it took another like 13 years for the last bit to come about. Here we go. So in 1932, Rutherford demonstrated the existence of neutrons, right? And they're neutral. They don't have any charge, right? And so they were the last to find because they're the hardest to find because they don't interact. Positive and negative will interact, but neutral, it's aloof. And then this was the postulate of Dalton's atomic theory that we showed was wrong. It was this idea of isotopes, right? Atoms with the same number of protons, but different numbers of neutrons are isotopes. And we're going to look more closely at those in this course. But for right now, let's take a breath and say, okay, so what have we learned since 1932? Well, we've learned a lot, but for these 3 subatomic particles, we're in pretty good shape. Right? We have the electron, the proton, and the neutron. Right? We found the electron first. It had negative charge. Right? Then Rutherford found out that protons and electrons had equal and opposite charge. And of course, the neutron is neutral. Now, mass, we're just going to arbitrarily give the electron a mass of 1. And if we do that, the protons are almost 2,000 times heavier. And the neutrons are slightly more heavier than the protons, but this, for our purposes, this is enough. So basically what this tells us is that the electron mass is negligible. We can really ignore it. When we're looking at the mass of an atom, it's the protons and neutrons that create the mass. Okay, so now we need some terms to describe atoms so that we can compare them. All right, so for atomic number, we're going to use the symbol Z, and so that represents the number of protons in an atom. All right? And so the atomic number is unique to each element. So if I'm an element and I only have 1 proton, I have to be hydrogen. Atoms with only 1 proton are always the element hydrogen, right? This is how we know what element we're talking about. Now, the mass number, that we gave that the symbol A, and just remember I didn't make up these symbols. I thought they were kind of goofy too when I was learning them, but here we are. All right, so that's the number of protons plus the number of neutrons. And we see that that makes sense, right? Because when we look at the structure of an atom, it's the protons and the neutrons that create the atomic mass, right? So mass number is a good name. Okay, now isotopes. All right, so isotopes, right? So we talk about isotopes of an element. Okay, so right, so if we're talking about isotopes of an element, that means atoms of the same element, right? So that means they have to have the same Z, same number of protons, right? But different, what, right? Different values of A. The protons plus the neutrons, right? So if this is the same, right, what's varying? In isotopes, right, this is what varies. The number of neutrons, oops, let me slide this up. It's the number of neutrons that vary. That creates differences in the mass number, all right? So, and we will talk more about isotopes in the coming videos. So I don't want to say too much now because we'll get to more. All right. So then let's put this all together, right? So we'll go the nucleus. We'll put that in the center, right? There's our nucleus. So when we see the nucleus, right, we see that there's going to be protons and neutrons present, all right? And this is what creates the mass of the element. And then the electrons, right, they're up to a mile away if the nucleus was the size of a grape, right? And so here's the electrons, the little muffins or raisins, right? So what do the electrons do, right? They create the size. Okay, the size, that might feel like the volume. You could think of it as the volume as well, right? So when we think about matter, right, we're thinking about mass and volume. And so we want to link that to our atomic structure. So let's look at that on the next page. Let's bridge this together. Let's link the microscopic and the macroscopic together. Okay, so atoms are the building blocks of matter, and matter is defined as anything with mass and volume. All right, so what's the relationship between atomic structure and matter? All right, so if we're looking at, how do I want to do this? I want to do atoms, right, and matter. So atoms build matter, right? So it's the protons and neutrons in the atoms. Those create the mass of matter, and the electrons create the volume of matter because the electrons create the volume of each atom. So now let's look at how this information is communicated to us on the periodic table. Okay, so if we look right above each symbol, we see a whole number, right, increasing by 1. All right, these values, these are the atomic number. This is Z, the atomic number. And remember, what is that, right? That's the number of protons. Okay, now we have all the symbols. Now underneath, I know this is very hard to see, but you have your copy that you're working with, right? We have all of these numbers down below, and these numbers down below, they're not really whole numbers. What are these? These are the average atomic mass of each element. And the reason why they're not whole numbers is, remember that we have isotopes, right? And the isotopes occur in different amounts. And so the isotopes and their abundances are what we use to calculate these average atomic masses. And so we'll be looking at that in a future video. But for now, we just want to get our bearings and get introduced to the periodic table and start to recognize all the different types of information that it communicates with us. Okay, so now let's have a little bit of a wrap-up page to make sure that we understand the main points of this video. All right, so here's our last page for this video. All right, now keeping the terms straight is really the path to mastery, right? So when we're talking about atoms, that's definitely microscopic, right? And if we're talking about elements and compounds, that's macroscopic. Okay, so, right, the atom, right, so the atom is the smallest piece of an element, right? So just think back to Democritus, right, the atmos. So it's often we can communicate with atoms and elements kind of synonymously, but they really are different. And then remember that compounds then are the fixed ratio of atoms that form a particular compound, right? So these are all defined for you here. So let's make sure we feel really confident on this, right? So when we look at water, right, here's our formula subscripts, and we don't show the 1, it's understood. So this is telling us we have 2 hydrogen atoms to 1 oxygen atom. All right? So the ratio of hydrogen to oxygen is 2 to 1. Okay, or let's look here, right? So this is glucose. Okay, so if we look at glucose, right? So looking at those formula subscripts, right? So we would have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. All right, so the ratio of carbon to hydrogen to oxygen is 6 to 12 to 0. All right, so looping everything together that we've learned. Now, let's look at one more thing. All right, so if we look at calcium phosphate, how many elements are present? Right, so we have calcium, phosphorus, and oxygen. So there's only 3 elements present, but how many atoms? Right, so we look at our formula subscripts. So we have 3 calciums. Treat this mathematically, right? We have 2 phosphates, so we're going to have 2 phosphorus atoms. And then we're going to have 2 oxygens, or 2 sets of phosphates, so that would be 8 altogether. So 5 plus 8 would be 13. So we have 3 elements present, but 13 atoms. Okay, well, that concludes our introduction to atomic structure. Take some time now to review these notes, make sure they make sense, and work a few practice problems to reinforce your understanding.